class. Yeah. Sorry. Empathize.
All right, everyone. So we figured that we'd start today with just a quick overview of the hints for homework 2. These were posted as of last Friday, but just wanted to do a quick overview of them, seeing that your homework is due on this coming Friday. So let's first just talk about the algorithms that we gave you. We gave you serial, MPI, OpenMP, and pthreads implementations. Now, what do all of these do? All of these compare every single pair of particles, so they have over n squared interactions. And for the particle that you can see there in blue, even though it only has one neighbor, I have to check all of the different particles in order to figure out what the interactions are. And most of the comparisons are way outside the interaction radius. The OpenMP and pthreads algorithms, they just simply split the particles up evenly, and then they just take advantage of the fact that we're on shared memory, and they check all of the different particles again. And the MPI actually does an all gather, so that it actually grabs all the particles and puts them together. None of these are optimal, and just throwing parallelism at something isn't going to make it to go better. So first, you have to improve the serial algorithm. And the big idea for the serial algorithm is that you have to take advantage of the locality of the interactions. So for the big idea here is to do binning. And that means that for a particle that we have, which is the blue particle, I don't really have to check all of those other particles in this area. I don't have to check any of them. If I do a sort of local binning, which means that I place each of the particles inside a local interaction, I only have to check my local neighbors in order to figure out what particles I can possibly interact with. So doing this sort of approach will reduce the complexity from an order n squared to, for each particle, I have to check my bin and the neighboring bins. And so if we assume d to be the number of particles per bin, then the total complexity becomes order n times d times 9. And how large can d be? This depends on the size of the bins. And if you choose the bins smartly, so if you choose the bins to be a bulk cutoff, there's not that many particles that can be inside one of those bins. And this is why you can get an order n algorithm without having to go through all of the complicated approaches of Barnes-Hut or fast multiple methods that are out there.
And which you'll hear about later in the semester.
Now, this is a very good idea, but how do you actually go about implementing this? Well, the devil's in the details, which is why giving you the theory is all right. So, how do you actually implement those bins? There's multiple options. Two of them is that you basically clear the bins at every step and have to rebin the particles. The other ones is that you keep the bins around and just take care of particles that move around between bins. And there are plenty of common problems that come up with this approach. Basically, in case you're seeing that in case you're using the visualization code and you're seeing that the particles are accelerating, that basically means that the particles are not interacting. So the correctness check that we give you only works for the interactions that you use. So if you don't call apply force at all, actually the check for the minimum distance won't give you any useful answer. So you also have to be careful of that. So the general idea is here, and how you implement this is up to you, and how well you implement this will determine how good of a serial algorithm you manage to get. Now, in order to move from this to a shared memory implementation, there's actually not that much that you have to do. You just have to check what are the moments in my code where I could have two different threads accessing the same trying to write to the same location. And this is very important because it's just the writes that will actually give you a race condition, not the reads. So if you go through your code, you're going to see that there's very few places where you actually have to, where after you include parallelism with just pragma OMP4s, you're going to see that there's very few places where you actually have to ensure that multiple threads don't write to the same location. And making sure that you don't get deadlocks, that meaning that all of the threads do get some progress is important. If you don't put any locks whatsoever, I guarantee that you will get inaccurate results. And not all the time, but some of the time, which is bad. And the one thing, just because you write correct OpenMP code does not mean that it's going to go faster than serial. There's plenty of ways to write excessive synchronization that will make you actually go slower than serial. So you also have to be careful, and I would say get correctness first and then see how you slowly can reduce the amount of synchronization that you have in your code. For an MPI implementation, you have to do something a little bit more different because there is no common idea about what my neighbor is, meaning that for the particle in blue, for example, I have to check it with these 3 boxes that live here. Those 3 boxes, I don't have them on my local processor.
So there are 4 processors in this picture.
Yeah, so in this picture, there's 4 processors, and they're split by a domain decomposition. And the idea here is that I have to be careful, and at each step, that did not work.
Okay.
So I have to be careful, and at each step of the MPI algorithm, that's too much.
Yeah.
So the idea is that at each step, I have to communicate to the particles that live on my neighboring processor. So in order to get the correct result for the particle in blue, I have to be careful that I actually get the 3 particles in the lower part. And these are what we referred to initially as the ghost zones when we talked about the particle methods. So you can take a look through the presentation to get a better idea about what the other problems could be.
Which is posted.
And the PowerPoint is posted in the resources, both the resources page of the homework assignment and also on Piazza. And so if you have any questions, you can also reach me after class or during office hours. And now I'm going to hand it over to Jim so that he can continue with dense linear algebra.
Are there any questions first? Okay.
So you posted OpenMP tutorial, right? And there was some issue that it was just showing 1 thread and not n threads. So I figured out that the C flags was not set to OpenMP. Actually, LD flags was set to OpenMP. That's why it was not showing multiple threads. So that was the problem.
We'll make sure to check that in the right one and post an update. And we have another question.
Yeah, sorry. Do you know good ways to parallelize the creation of the bins? Because you have to write, you have to decide which particle is going to go into a bin. So it just involves a lot of writes to a data structure, which are generally have tons of race conditions.
So if you do a sort of spatial decomposition to the problem, then you can do the binning locally at each step, and you have to figure out a way to initially split the particles up, but that only happens at the first step. So if you do a spatial decomposition, then at each step you can have each processor only be responsible for its domain, and that will ensure a parallelization practically of the bin creation for the MPI code. Are you asking about the serial OpenMP code? So I mean the bin creation themselves doesn't. So are you talking about the clearing of the bins?
Deciding which particle goes in what bin.
So the question was about deciding which particle goes in what bin. And the idea is that you can have multiple threads add particles to bins. You just have to be careful that in the case that you have two threads writing to the same bin, you have to make sure that you actually lock it so that you don't get a race condition. Yes, using fine-grained locks is the way to do this, and make sure that you have multiple locks. You don't just have one lock per the entire algorithm, because that's actually one of the things that will give you slowdown versus serial.
But this should probably only be an issue for the initial creation of the bins and not later.
I actually believe that it's going to be at every step, since you have to do the allocation, the binning at each step. You will get...
If you choose to do it that way.
Yes, if you choose to do it that way, right.
Any more questions? Okay.
So how expensive is it to have a lock? So if you have like n bins locks, is that a lot of overhead?
So just having a locks, there's some overhead, but as long as you don't have multiple threads waiting for locks, it's actually going to be relatively okay. It's, I mean, it's still not going to be optimal. So I mean, the best way to do it is that for the threading model, you still do a spatial decomposition, and then you just use shared memory to access the stuff on the side. But doing it with locks should give you speed up. And I mean, there is some overhead, but it's not that much. You know, it depends on the implementation. That's why I say that. There's no right answer.
There is a for loop on number of steps as well. So is there a way to parallelize that as well, or should we not think about that?
So if you look at the code that we gave you, actually the code is parallel there. It's not parallel between iterations, because every iteration has to have,
There's a whole field of research called parallel in time. And we're not, and so you could Google that if you liked, where people do try to do that. And one thing you could imagine is you move particles forward, and perhaps, you know, assuming that you haven't missed anybody, and then you could say, oops, I forgot to interact with someone, because they got close, and then you could back up. We talked about that kind of speculative asynchronous kind of stuff earlier when we talked about simulations. But yeah, so just look at parallel in time.
I would not suggest that for the homework.
Yeah, not for the homework though. Okay. So there's a huge design space for this very simple assignment. You don't have to explore all of it. So I almost finished the last lecture. I have like 2 or 3 more slides about matrix multiplication before I go on and then use that to talk about other dense linear algebra algorithms. So let me just quickly review what we learned about classical matrix multiply. I have an n by n matrix multiply on p processors. And so the complexity, I have perfect load balance for the flops. Every processor is doing n cubed over p flops. Now, what's the other part? How much do they have to communicate? There are 2 metrics of success there of cost. How many words do I move? The total number of words, and the total number of messages, units of words that are packed together. And these are the 2 lower bounds that I wrote down before. And because I want to compare this to Strawson in just a moment, that's going to be the next issue, I'm going to write this in kind of a funny way. So it's the number of flops divided by the local memory that you use to the 1/2 power. And I'm just going to write it that way, just for fun. You'll see why in a moment. The lower bound of the number of messages is this. It's exactly a factor of m smaller. That factor of m goes away because the fewest number of messages you can send is they're all as big as possible. They fill up the memory. So the question is, how long can this wonderful go? How long can I keep making m larger and larger and keep going faster and faster? Well, I have to have, well, m has to be at least big enough to have 1 copy of the data. So it at least has to be 3n squared over p to store 3n by n matrices. But m can keep growing. And how much can I keep growing it before this decrease stops? I can go up to p to the 1/3 copies of all the data. So I can store not n cubed over p, n squared over p, but a factor of p to the 1/3 times larger. And then you hit a sort of a global lower bound. And when you get that far, my communication drops all the way to, sorry, that should be n squared over p to the 2/3. N squared over p to the 2/3. So now let me contrast that to Strawson. So I'm just going to have Strawson side by side with all of these. So just let's remember, what does Strawson do? Instead of doing the sequential algorithm doesn't do n cubed floating point operations, it does n to the omega, where omega is log base 2 of 7, about 2.81. And it was a divide and conquer algorithm. I won't repeat it. And it turns out you can get perfect parallelism in Strawson too. So n cubed over p becomes n to the omega over p. So what about the communication? So the reason I changed the format here is that all I have to do is change 3 to omega. So the lower bound for communication for Strawson is also lower by decreasing this exponent from 3 to omega, just as I decreased it there. Now that made the typesetting very easy. The proof is much harder. And so I won't go through the proof, but it uses a bunch of interesting graph theory. So we also have the potential of communicating a lot less and a lot fewer words. The same thing happens to the number of messages. It's also smaller by a factor of capital M. And so the question is, how long can I keep using more and more memory, right? This benefit can't go on forever. And instead of going up to p to the 1/3 copies, it turns out to be p to the 1 over 2 divided by omega. If you happen to plug in omega equals 3, they agree. So this is sort of the general theorem, not just for Strawson, but for Strawson-like algorithms, because there's a whole family of these things that have happened up. And so how far can you go? Well, again, that should have been n squared. N squared over p to the 2 over omega is the absolute lowest number of words you can communicate, no matter how much memory you have. And so that's the comparison. And I'm pleased to say this won another Best Paper Prize. So now let me show you the performance in practice. So I'm going to show you a strong scaling plot. And so this is a very large matrix multiplied on Hopper, so 94,000 by 94,000. Going on all the way from 49 processors. Why 49? Well, 7 squared, no surprise to make Strawson convenient, up to many thousands of processors. The vertical axis is the effective gigaflops. So the way to, because what I'm going to do in this plot is compare Strawson to classical, right? So flops is not exactly the right thing to count. I want to compare runtime. And so in fact, the vertical axis is reciprocal runtime, so up is good. And the way I scale it is I just assume all the algorithms do two n cubed floating point operations. But really, it's proportional to 1 over time, so up is good. And so I have a whole bunch of different implementations here. The bottom line is the classical summa algorithm that I told you about last time. And that's getting this many floating point operations per second. And it scales pretty well in this range. And so that means I'm doing n cubed operations, not doing any redundant memory. Here is the 2.5D matrix multiply that I told you about last time, where I use more and more memory. If I double the number of processors, I double the memory. And that's going significantly faster, although eventually the scaling falls off. Here's the peak speed of the machine. That is how fast any classical algorithm could go if communication were free. These blue lines are previous attempts to implement parallel Strawson that were in the literature. They didn't work so well. And then here's the new one. And you can see it's sort of horizontal for a while. That means it's scaling perfectly. If I have 7 times as many processors, I'm going 7 times faster. And eventually that does fall off near the top. So anyway, this is yet another implementation of matrix multiply. And there's all sorts of interesting ideas in the proofs, which I won't have time to go into. So why have I bothered? So to finish the last lecture, why am I telling you all this about matrix multiply? It's because it's a building block for everything else we do in linear algebra. And so here is kind of the software stack that the ultimate library, Scalapack, Scalable LA Pack, builds on. So there's sort of some of the software just runs on your local nodes, right? This is the sequential part. Some of it is global. It's the distributed memory part. So at the locally, we have the BLAS, local matrix multiply. We have the basic linear algebra communication subroutines, send this submatrix to that processor. Those are building blocks. On top of that, you have the parallel BLAS, so the parallel matrix multiply I just told you about. That's the building block. And above that, we have Gaussian elimination and least squares and eigenvalue problems that sort of just build on top of it. So I've spent all this time telling you about the BLAS and parallel matrix multiply because they're going to be building blocks for everything else that we do. So before I leave this topic, I want to tell you that these lower bounds and optimal algorithms that cover linear algebra were originally invented for algorithms that sort of smell like 3-nested loops. They actually generalize to kind of arbitrary loops. And so I just want to have one slide to sort of say how this generalizes. So this is beyond linear algebra. And so here is the theorem that I was using over and over again for linear algebra, which is, suppose I have an algorithm. I use matrix multiply. It could be Gaussian elimination, could be anything else. It does a certain number of iterations. It has an inner loop. Suppose I do the inner loop g times, and so n cubed for dense matrix multiply, and I have a fast memory of size m. Then the theorem says the number of words moved is the number of iterations divided by m to the 1/2. That was my theorem that I used over and over again. So here's how the extension works. So it works for any program that sort of smells like nested loops. You don't have to have just 3. You can have as many nested loops as you want. You have to access arrays. Arrays are the interesting things. I want to count how many reads and writes of arrays there are. You can have arbitrary numbers of subscripts. And they can be any linear functions of the array indices that you want. So you can have arbitrary messy stuff down there. And so that's what your code looks like. Then it turns out that there's another lower bound that looks almost the same as this one. It's lower bounded by the number of times you execute the inner loop divided by m to some magical exponent. The magical exponent was 1/2 for matrix multiply. But it's going to be something else depending on how many loop iterations you have, how many arrays, and what all these funny linear functions are. And it depends on a recent generalization. So how did we prove this for linear algebra? There's a classic theorem from geometry from 1949 from Loomis and Whitney, which let us do this. And there was a recent generalization of this using functional analysis and group theory and all sorts of things by a team of pure mathematicians who weren't thinking about computer science at all. It just happened to be what we needed. That let us give this magical exponent and a lower bound for kind of arbitrary looking code that accesses arrays. And there's a lot of different examples. So linear algebra, n-body, database join, a lot of code is represented by arrays. And so there's a lot of open questions about how to generate these. And if there's time later in the semester, I will talk about it. But that's just sort of a summary of where all that stuff goes. But I won't do any more details right now. So now what I'd like to do is switch to Gaussian elimination in particular, if there are any questions. Okay. So what I'm going to do is remind you of the sophomore version of Gaussian elimination and convince you that it's really just 3 nested loops. And then I will begin optimizing it and tell you what it takes to actually hit the same lower bound that we did for matrix multiply. So first I'll tell you how to, so the classical version we all learned as sophomores basically adds multiples of one row to the next row to create a 0 somewhere and does it over and over again. That is most naturally expressed as a BLAS1 operation. That's going to go very slowly. As we know, BLAS1 is really slow. So what I need to do is reorganize it so I spend as much of my time as possible doing matrix multiply, BLAS3. And so I will tell you how to do that. And that algorithm has been around for a while. Whenever you type A/B in MATLAB, you're using our code, and it's been doing that for a long time. It turns out that does not minimize communication. There is, we realized that just a few years ago. And so there's some new algorithms that are in the works that do minimize communication and can go much faster. And so I will tell you about those. And so I'm going to tell you in particular about one that minimizes the bandwidth. It turns out you can also minimize the latency. It's more complicated, probably won't do the details. Then I'll go to the parallel case, and I'll remind you of all the different data layouts. How do you decide which processor owns which submatrix? And I'll tell you about parallel Gaussian elimination, the way it works now, which is in the Scalapack library. And again, I will point out that it's been there for a long time, but it doesn't minimize communication. It actually minimizes bandwidth, but it's terrible at latency. And I'll tell you about the new algorithm that does minimize latency as well. And what's interesting here is that in contrast to matrix multiply, where I did exactly the same arithmetic, just in a different order, here I need a different numerical algorithm. It turns out I have to abandon partial pivoting. Partial pivoting is what you may have learned about, is how do you decide which row to eliminate next. That provably cannot hit the communication lower bound. We need a new way to decide how to order the rows. And I will tell you about that. And then I will very quickly summarize the rest of dense linear algebra. It would take more than one lecture to do that. I'll just give you a few tables to say what's possible for everything else, least squares, eigenvalue problems, and so forth. And at that point, we will probably have time left for just one thing. And so I'll probably ask for a vote. we can talk about a little bit more of the detail about how do you make all this work for multi-core. What are the software tools that people use to do all this scheduling, all these tasks in multi-core? We could also talk about it for GPUs. And we could also go back and do the proof of the lower bound if anybody wants to. So when we get here, if there's time left, we'll take a vote. So here, let me remind you of what sophomore Gaussian elimination is, and then optimize it in a few slides to get to the version that's fast. And so here's the picture, here's the code. And so at every step, what I'm going to do is take multiples of a row and add it to subsequent rows to 0 out below the diagonal. So first I add a multiple of the first row to the second row to create a 0 there, and so on and so forth. Then I take the second row, add multiples to what follows to create zeros there. And so here's the code that I'm going to start with. For each column, I'm going to 0 it out below the diagonal by adding multiples of it to later rows. So I'm going to loop over all the columns where I need to 0 out, I going from 1 to n minus 1. Then I'll loop over all the rows that come underneath it. So j is the index of the rows, so I plus 1 to n. And I need to add a multiple of row I to row j. What's the multiplier? Well, here's the multiplier. And here, this final innermost loop, so I have 3 nested loops, just like matrix multiply. I'm adding a multiple of row I to row j to create those zeros. OK, so that's going to be my starting point. And what I'm going to do for the next few slides is I'm always going to take the code from the previous slide, copy it to the top, do one optimization, and get to the next version until I get to the final version. So the next slide will just copy that, and it appears up here. And so let me do a sequence of simple iterations. So the first thing to do is that this multiplier in here is the same for all values of k. So why don't I just compute it once and reuse it, right? So let me just hoist it out of the inner loop. I'll call it m for the multiplier. I'll do that division once, and I'll do the multiplies there. And here's the picture. I take these two numbers, I divide them, get the multiplier, and then multiply that row to create the 0. OK, that's simple enough. So there's the code I just did. The second optimization is don't compute what you know. And what do I know? I know I've created all those zeros. So let me not bother to do that. And so I'm not going to add this entire row to that row. I'm going to start over there. And so instead of looping from I to n, I'm going to loop from I plus 1 to n. And so I'm going to leave all those filled up. So that's the next version. Now it turns out that those entries are actually going to be useful. I'm going to use them later. So what I'm going to do is take that multiplier and just store it in the entry that I would have zeroed out, because I'm going to need them for the rest of the algorithm. So that multiplier up here, m, is gotten by dividing aji by the diagonal. I'm just going to stick it back on top of aji and use it right there. So that doesn't change the code at all. So now the bottom of the matrix is filling up with all these multipliers. I'll tell you why they're useful in a moment. So there's the code again. And so the next optimization is I'm going to take this, and I notice I'm actually doing two different things. This line of code is dividing the column of the matrix by the diagonal. So let me just do that first, compute all the multipliers in one loop. And then independently, once I've gotten all the multipliers, do all the subtractions of one row from another. So all I've done is I've split this loop, j loop, into the first j loop and then the second j loop. OK. So finally, there's the last version of the code. And I recognize that this loop is really a call to the BLAS 1. So this is a single subroutine call. What am I doing? I'm taking this column of the matrix, and I'm dividing it by the diagonals. So that's a single BLAS 1 call. Here I've written it in MATLAB. So it's a single line of MATLAB. And what about these two nested loops? That's where most of the work is. This is really what's a BLAS 2 call. It's a rank 1 update. I'm taking this column vector, multiplying it by that row vector, and subtracting it from that square matrix. That's what this doubly nested loop is doing. So let me write it here in MATLAB, which says take the matrix in rows and columns I plus 1 through n, take the column over here, the row there, multiply and subtract. And so this is really 3 lines of code when I write it in the next slide. So here's the picture to see how the algorithm is making progress. At the I step, I have finished all these multipliers. That's all finished. I've finished that part of the upper triangular matrix, and I'm updating the trailing part. OK. So let me write it there as 3 lines of code. There's Gaussian elimination. And so what have I actually done here? Let me now use those multipliers and tell you what I've done. So let M be the strict lower triangular matrix, the place where I've stored all the multipliers. And let me implicitly stick 1s in the identity. So I don't actually form L because I just sort of implicitly know put 1s in the diagonal. So that's a lower triangular matrix. And let me call U the output. That's the upper triangular matrix. then the lemma, which you can prove for yourself if you like, says that what I've done is I've factored my original matrix into a product of a lower triangular matrix times an upper triangular matrix. So that's what it looks like. I factored A into L times U. So that's what the algorithm actually does. And that's what we use to solve AX equal B. So 3 steps. I run the algorithm I just described, and I factor A into L times U. That cost me 2/3 n cubed. That's where all the work is. Now, how do I actually solve AX equal B? I have to do 2 triangular solves. So first, I'm going to solve a triangular system with the lower triangular matrix, just using substitution. That's cheap, n squared. Then I solve another triangular system with the upper triangular matrix, again substitution, n squared. And just to convince you that I have actually solved AX equal B, let me multiply A times X, substitute L times U for A, substitute U times X, Y equals U times X, and then L times Y equals B, and I'm done. So this is the way people solve it. Now you may ask, well, why don't you just compute the inverse of the matrix and multiply it by it? That's a bad idea for 2 reasons. It costs 3 times as much as doing it this way, and you get a worse answer. It's much less numerically accurate, so don't do it. Don't compute inverses. Okay, so this has 2 problems. It's this 3 lines of code. There, I put them up there again. The first problem is, what if I divide by 0? So I have to deal with that. Or if I divide by a very tiny number, I can get into trouble too. And the other thing, of course, is that I'm spending all my time doing BLAS 1 and BLAS 2, which means I'm running at a tiny fraction of the peak of the machine. Here's the plot I've shown you before. I'd really much rather run near the peak of the machine, which I have to do matrix multiply. So I have to reorganize all this to do matrix multiply. So let me fix those 2 things. I'll tell you the classical fix first, which is what most code uses, even though it cannot hit the lower bound. Suppose I try to run that algorithm on this matrix. That's a pretty easy matrix to solve. I'll immediately try to divide 1 by 0, and things won't work. So what I need to do is, when I see that I have a 0 on the diagonal, is I have to change the order of the rows. And here I just swap the 2 rows. And then I get a nice big number in the diagonal of 1, and the algorithm works just fine. So that's the cure. And let me now write the code and tell you what I am implicitly computing. So the black lines are the same 3 lines I had before. And all this red stuff simply says, every time I get to a certain column, look down on the diagonal and below, find the biggest guy in absolute value, and record where he is. Now, if the biggest guy in the diagonal is 0, you know you have a singular matrix. And at that point, you can probably return with a warning message, or you could continue computing. There are some reasons to do that. But in principle, you have a singular matrix, so you might quit. And otherwise, just swap the rows. Put the biggest guy in the diagonal. And now, when you do this division, you're guaranteed that the denominator is bigger than everybody in the numerator, and each quotient is less than or equal to 1. And you can prove that numerically you're in good shape. And so I don't compute, however, A equals L times U anymore. I have a slightly different factorization. What I've done is I've factored my matrix into the product of 3, a permutation, which is just reordering. That's a very, a list of, it's a permutation. It's very simple to represent, times a lower triangle times an upper triangle. And then you can go ahead and solve your linear system. It's very simple. And this is sort of the basic code that's in, A\B and so forth, this particular numerics. So, but it doesn't have very good performance. And that's because it is spending all its time doing BLAS 1 and BLAS 2. So that's the next thing we have to fix. And somehow reorganize it so it's spending all its time doing matrix multiply. And so the idea is what we need to do is blocking. Now, when we did that for matrix multiply, it was pretty easy to see what to do. I took square blocks that fit in cache, and I multiplied them. But if you look at Gaussian elimination, I'm sort of going column by column or row by row. It seems like to get to column 2, I need to know column 1. Where do I get these dense matrices to multiply? And here's the simple big idea that's going to work not just for Gaussian elimination, but for everything else. It's called delayed updates. So what I'm going to do is, yes, column 1 has to update column 2, but I don't have to update column 100 yet, right? I can wait. And then I can update column 2 and 3. I won't update column 100. What I'm going to do is save up a whole bunch of columns and apply them to the rest of the matrix, columns 100 through n, all at once. And so when I do that, when I apply them all at once, that looks, no surprise, like a matrix multiply. So by saving up all the work and doing it all at once, it turns, and I'll show you the code in the next slide, it turns into a matrix multiply. And so if I choose the sizes correctly, I can spend close to 100% of my time doing it that way, and that's good. And it turns out the same idea works for a lot of dense linear algebra, so least squares problems. It doesn't work if you try to do eigenvalue problems or the singular value decomposition, you can get about half BLAS3, and the other half is still BLAS2. So we'll need some other ideas. So here's the approach. So what I'm going to do is pick a block size, and I'll show you the code in the next slide. That's how many columns I do all at once and then apply them all at once later. So I'm going to save and apply B updates, and B should be small enough so that I can fit my whole B columns in cache at a time. And it should be large enough so that when I do a matrix multiply later, it runs fast. But so let me show you the code. So what I'm going to do is I'm going to take my matrix and process it B columns at a time. So my outermost loop is going to go from 1 to B plus 1 to 2B plus 1 and so forth. And so let's suppose that I've gotten to this point in the algorithm, and I've finished computing all those multipliers. I've finished computing all of those entries of U, and I'm now working just on the trailing submatrix. So here's what I'm going to do. I'm going to just work on these B columns. I'm going to do all of these B columns first. And so what I'm going to do first is take the algorithm I just showed you, which is all BLAS1 and BLAS2, and take this tall, skinny rectangle, there it is, and factor it into L times U. So it's the same algorithm as before, BLAS1 and BLAS2, and that's a lower triangular matrix. It's okay, it has more rows, and there's an upper triangular matrix. And so, so that's what I'm going to do. And so here, I'm going to overwrite this submatrix with L times U, the lower triangular blue times the upper triangular brown. Okay, so just call that thing I had before as a subroutine. So the next thing I need to do is get this part of U, the pink part. So let me just give a name to this lower triangle. So there's a lower triangular matrix, LL. And what I need to do now is update this, and that turns out to be a triangular solve. So I need to multiply LL inverse times all those columns. That is a BLAS3 operation. So if I were just doing a single triangular solve, it would be BLAS2. But if I have lots and lots of columns, it runs just as fast as BLAS3. So this is a single call to a BLAS3 subroutine. Solve a triangular system with this triangle and all of those right-hand sides, all of those different independent columns. And I update the pink matrix. So that, finally, that's all small potatoes. That's not where most of the work is. Now I do all the real work. I need to update this last big part, and that's the matrix multiply. I multiply the blue matrix times the pink matrix and subtract it from the green matrix. That's a single call to the BLAS3. That's where all the work goes. And if B is big enough, then that runs at full speed. Okay, so that is the algorithm that's been around for a while. But I need to pick B carefully to make this work. So let me just show you some performance data. And so this is on some old machines. I'll show you some more modern machines in a little while. And so what I have here is the efficiency, so up is good. And I have 3 different plots to sort of say, am I getting close to peak performance by doing it this way? And I'm going to measure that in a few ways. One, so let me first of all, say matrix multiply is my inner loop, so I can't go faster than that. Let me just compare matrix multiply to the hardware peak. That's the green line. And you can see that's getting, except for that processor, a pretty high fraction of peak. So that's good to have as an inner loop. That's the green line. So now let me compare the speed of LU that I just showed you to the speed of matrix multiply, right? I can't go faster than my inner loop. And so that's going to be the red line. And you can see that it's getting, 80%, except for that platform, 70% of the speed of matrix multiply. So I'm going 70% of what for me is the peak. Now, why did it drop dramatically from there to there? It's the same machine, actually. It's a Cray C90, except up here, it's 1 processor, and here, it's 16 processors. So it's the same machine. And the trouble is that I can't keep 16 processors busy on these little matrix multiplies. So it's just the fact that the communication in the parallel matrix multiply is making me drop from 95% down to 50%. But otherwise, it looks good. And then finally, the question is there a different way to do a different way to do LU? So here's one more plot of the speed of the algorithm I just showed you divided by the speed of the best effort at all these companies where they had a team of programmers trying to make it run as fast as possible. And that is the black line. And you can see that it gets a decent fraction of the peak, but we all know there's lots more tuning that you can do. And so that tells you, yes, there's a little bit more. I haven't told you the whole story. But it's getting you a decent fraction of what carefully hand-tuned code can do. So now the question is, can we do better? Obviously, that's why we're all here. And so let me, first of all, in one slide, convince you that if I have a lower bound for how fast matrix multiply can go, it's automatically a lower bound for how fast Gaussian elimination could go. So here's the idea. I can embed matrix multiply inside of Gaussian elimination. Suppose I take this matrix and where I have an A and a B in it, and I do Gaussian elimination. What's the answer? You can just multiply these two matrices together and you'll see that they work. So there's L, there's U. What's inside U? It's A times B. So that tells me if I have an algorithm that does Gaussian elimination, it has to be able to do matrix multiply. And so if I have a lower bound on how much matrix multiply has to communicate, and I do, then I have a lower bound on how much Gaussian elimination has to communicate, because it's embedded inside. So I can hope to do as well, right? That's going to be my goal. So the natural question is, does that algorithm that I just showed you, I'm just copying the code from before, it's the same code, does that minimize communication? So let's see. So the easiest case is when the matrix is enormous. When it's so big, when the dimension is so big, not even one column fits in fast memory. That's a really big matrix. And the answer is yes, it attains the lower bound. And that's because if you pick the block size to be the square root of the cache size, same as for matrix multiply, you're spending all your time in the matrix multiply and life is good. The other case where it works is if the matrix is so tiny it fits entirely in cache, well, of course, it minimizes communication because you just read the matrix in once, do anything any way you like, write it out again. That you can't do better than that. But so this is for super tiny matrices. This is for really perhaps impractically large matrices. The interesting case is in the middle, and it's not optimal. It can do arbitrarily more communication than necessary because you can't choose this block size to simultaneously make the matrix multiply go as fast as possible and to do the factorization of the tall, skinny matrix. And so how much worse than optimal can it be? A factor of m to the 1/6 power. So that's sort of the theory. So now the question is, how do I reorganize it to actually hit the lower bound? And I'll show you the sort of simplest algorithm first. And I'm not going to worry about pivoting. That's going to come later. And it's going to be a divide and conquer algorithm, very similar to the one that we did for matrix multiply. So remember, I did a matrix multiply where I just divided the matrix into 4 blocks of half the size and multiplied those recursively. So here, the algorithm is going to be dividing the matrix in half again, but just the left half of the columns and the right half of the columns. So here in one line of English is the algorithm. Divide the matrix in half, left and right, do Gaussian elimination, LU, on the left half of the matrix, and then do it on the right half. So, but let me now write down the code for how that works. So this is going to be recursive LU. That's what our LU stands for. And so here's the base case. If I have a single column, that's very easy. L is just take the matrix, divide by the diagonal, and U is just 1 by 1. So my matrices are going to be rectangular, right? So even if you put in a square, when I divide it in half, I'm going to get tall, skinny matrices. So here is the first line of code. I'm going to divide my matrix in half, the left half and the right half, and I'm going to call recursive LU on this half here, and I'm going to factor it. And so I'm going to factor this part into the lower triangular times upper triangular by a recursive call of the subroutine. And then I will mimic the other algorithm. Let me just use L11 to be the upper half of that factor. And then what I need to do is update this. So I need to do a triangular solve, and that's a single BLAS3 call, L11 inverse times that block up there. So that's a single call to a BLAS3 subroutine. And then finally, I need to update the trailing matrix. So I multiply that submatrix times that submatrix and subtract it from the green one. And that is a one big matrix multiply. And then I'm almost done. I can call the subroutine recursively again and now do Gaussian elimination on that last corner and get L2 times U2. And then I have the answer. And so let me just write the code again at the top of the next page and convince you with 4 lines that it's optimal. So what I need to do is write down a recurrence for the number of words moved, W is the number of words, to do Gaussian elimination on an m by n matrix. And so let me just go line by line. What am I going to do? I'm going to call the algorithm recursively on a matrix with the same number of rows but half the columns. That's that call. So that's the same function on a problem of half the size. Then I do a triangular solve and a matrix multiply, and using the formulas I had before, I get that. And then I call it again on a smaller problem with n over 2 fewer rows, and again, half as many columns. And that's now a simple recurrence, and if I solve it, I get that it equals the lower bound with a, almost. It's the number of flops, mn squared is the number of flops divided by the square root of the cache size. And so that's a very simple way to convince you, except for a very small range, but it's close to optimal. Now the trouble with this is that I didn't tell you about pivoting, and if you actually just do the obvious way of doing pivoting, it all blows up. It doesn't work. And we only recently figured out how to fix it, and what it requires is changing the data structure over and over again, from storing your matrix by columns to storing it by blocks, and then back to columns and back to blocks over and over again. So at least in theory, we can now do everything for this, but we haven't implemented it. We've only written down, theory, so that could be a class project. Okay, so now let's go on to the parallel case, unless there are questions about the sequential case. And so let me just do it in a sort of high-level way first, and say that if I'm not worried about communication, then I can actually do it. There's an enormous amount of parallelism, too much if I want to actually be practical. So I need to identify enough parallel work, but not too much. I need to assign it to different threads. I need to worry about the communication. And I need to decide which processors execute which threads. And so if I just look at the BLAS2 algorithm, where I wasn't worried about communication, so the inner loop here, I've just repeated it, is I'm doing multiplying a column times a row, and so that's n squared independent multiplies, and I'm doing n squared independent subtractions. And so if I had n squared processors, I could do everything in 3n steps. But that's really too fine-grained, right? I'd spend all my time communicating the words, and so what I need to do is, figure out how to do this with a practical number of processors. So I need to go back and say, if I just have a few processors, how do I assign work? And so here's a picture I had for matrix multiply. I just want to remind you of what data layout we're going to use. So the simplest thing you could imagine with 4 processors is that each processor gets a quarter of the columns. And I've color-coded it here. So processor 0 gets the first n over 4 columns. But the trouble with that is, as I think I mentioned before, that's a bad load balance, because as soon as Gaussian elimination finishes the first n over 4 columns, processor 0 is idle, and so terrible load balance. So here, this will fix that, because now if I take any trailing submatrix with this cyclic layout, every processor owns about a quarter of the columns. That's good. So even if I'm over here, everybody has a quarter of the work to do. But I don't have any BLAS3 because they're all single columns, so I can't call matrix multiply so well. So I can try to compromise by not having single columns in the cyclic layout, but by having a block cyclic layout with a B. So now I can do at least B by B matrix multiplies, and the load is reasonably well balanced. But I now have a sequential bottleneck, because when I call Gaussian elimination on this block, there's one processor doing it. That's going to be too slow. So here's a funny kind of layout that people have thought about. So it's called a skewed layout. So if you look at it, processors, all P processors own the first block, and then I circularly shift them by 1, and then I circularly shift by 1. And so this is good for several reasons, or apparently, because if I take any trailing submatrix, then it's pretty decently load balanced. Everybody owns a quarter of it. I mean, this is too small to see that, but I mean, basically everybody owns a quarter of any subblock. But I also have P processors owning each column and P processors owning every row. So I have as much parallelism as possible, for this particular process. But it kind of makes everything else complicated to have matrix multiplies with this kind of funny layout. So it turns out we don't need to have p-fold parallelism to hit the lower bound. It's good enough to have much less parallelism. So I get to have a much simpler layout. And so I'm going to use a 2-dimensional layout, but it can't look like this because, again, I will have bad load balance. And so here's the winner. It's called a 2D block cyclic layout. I divide up the matrix into little b by b blocks, and I assign them to, in his case, 4 processors, and I just repeat that pattern over and over again. And so now, if you look at what processor 0 owns, it owns about a quarter of every submatrix, so the load balance is good. And this column is shared by the square root of p, 2 in this case, processors. So I have a decent amount of parallelism in every column, and that's going to let me hit the lower bounds. So now, given that layout, let me show you the algorithm that exists now, which does not hit the lower bound, but let me just show it to you anyway, because it'll be our starting point. It'll take 2 slides. So this is a scale-pack algorithm, and I've written out all the loops, and I've also shown you the picture of what each line of code does, which may be easier to follow. So here's my matrix, and I have, let's say, a 4x4 grid of processors. Let me suppose I've finished doing all that, so that part of L is done, that part of U is done. I'm now working on that. So I need to do LU on that panel, okay? So what do I need to do? I need to, once I've gotten, let's say I've finished that column and that column and that column, I'm now on this middle column, I need to pivot. So I need to find the biggest guy in that column and permute him to the top. That is a max reduce, right? It's a single call to a reduction routine that says, please find me the biggest guy in absolute value. And so I look at all those. And so that black line indicates all the data that's part of the reduction, and those 3 processors are participating. So that's the first line of code. The second line of code says, well, if the biggest guy is down here, I have to swap him up there. And furthermore, I have to broadcast him to all the other processors because everybody's going to need to subtract a multiple of that row from everybody else. So here I have, I have a point-to-point communication and a broadcast of a row. That's the second line of code. Now, the third line is divide by the diagonal, and everybody can do that. That's embarrassingly parallel. Divide by the pivot. The fourth line is please do a BLAS2 operation to update all of that. That's all embarrassingly parallel. Everybody owns their column and their row, and they multiply. So now when I'm done with that loop, I have finished doing LU on that. But nobody else, no other processor knows what I've done yet. I have to give them some more information. So the first thing I have to tell them is what rows have I permuted. So I do a broadcast to all these other processors in each row. So these 2 processors need to know what rows have I swapped. And so that is swapping information, just permutations left and right. And then everybody has to swap their rows with their neighbors so that all the rows are in the right order, not just in this column, but in every other column. Okay. Second and last slide of the algorithm. So now I have finished LU of this part. This was done. Now I finished LU of that block. I have to do my triangular solve. So I take this, what I called LL in the previous matrices, and I broadcast it sideways. Now this guy does a triangular solve, embarrassingly parallel. Each guy does a triangular solve with that triangle and its data. And it's finally time for the matrix multiply where all the work happens. I need to multiply the blue submatrix times the red submatrix and subtract from the green submatrix. And so there's some broadcasts, and then I can do the green stuff. And that last line of code is where all the work happens. So there's the lion's share of the communication, and there's the lion's share of the flops. So the question is, how good is it? Let me show you just some performance data on some old machines, and then I'll tell you why it's not quite good enough yet. So, let me just remind you, so I showed this slide last time just to remind you of how we expect things to scale. This is for matrix multiply. That's the inner loop. Then I'll show it to you for Gaussian elimination. And so these are a whole bunch of different machines. And what I'm doing is I'm showing you what fraction of peak they run at for matrices of size 2,000, 4,000, and 10,000, so bigger, and different numbers of processors, 4, 16, and 64. And the pattern was that if I fix the number of my problem size at 2,000 and increase the number of processors, I get a decent fraction of peak, 73% of peak, 63%, but it decreases, right? Because as I use more processors, communication becomes more dominant. I get a smaller fraction of peak. But if I fix the number of processors at, say, 64 and increase the problem size, then the n cubed flop starts to dominate the n squared communication, and the efficiency goes back up. So that's the kind of pattern I expect to see in Gaussian elimination. So let me show you the same data there. And so let's just look at this plot. And what I have here, it's sort of the same data, same machine, same problem sizes. It's the speed of Gaussian elimination, the way I showed it to you, divided by the speed of matrix multiply, because matrix multiply is my inner loop. It's the fastest thing I can do. And so here's the fraction of matrix multiply. And again, if I make the problem, if I increase processors, I go from 2/3 of matrix multiply down. But if I fix the number of processors and increase the problem size, it goes back up to a decent fraction of the speed of matrix multiply. And so that's the sort of behavior that we expect. Now, what if I just compare the raw running time? So what do we expect? So how many flops does matrix multiply do? It does 2n cubed flops. How many flops does Gaussian elimination do? It does 2/3 n cubed, right? So we'd expect if all we were counting as flops, it should be 3 times faster. Or this ratio should be 1/3. And so you can see, well, it never gets quite down to 1/3, but it gets down to like 0.4, for a large problem on a few processors. And sometimes it takes longer to solve a linear system. But if it's just counting flops, it should be 1/3 the time. Okay, and this has been the standard algorithm for a long time. And so let's ask, does it hit the lower bound? And since the answer will be not surprisingly no, what can we do to improve it? And so just to remind you, what is the lower bound for matrix multiply and for Gaussian elimination? If I only have one copy of the data, let me just start there. N squared over root p is the number of words, and root p messages. So what about scale-pack? What about the algorithm I just showed you? Well, it's actually not bad for the number of words sent. It's within a factor of log p of the lower bound. So, and since we have all these broadcasts and reductions, it's not surprising that there's a log p factor. On the other hand, it's terrible in the number of messages. There's a factor of n there. N can be arbitrarily larger than p, let alone square root of p. So why is this here? Well, remember, every time I get to a column, I have to find the biggest one in the column. And to do that, I have to do a reduction over square root of p processors. So I'm doing n reductions. So that's where the factor of n comes from. And a reduction is log of the square root of p, which is the same as the log of p. So as long as I insist on doing partial pivoting, this is going to be arbitrarily larger than the possible lower bound. So it turns out that what we have to do is we have to use a different numerical algorithm, and we're going to have to do abandoned partial pivoting. Of course, we have to pivot somehow. We have to somehow pick good columns, good rows to put up to the diagonal. And so what we're going to do is in one step, in one reduction, I'm going to pick not just one row, but b rows. So that's what I need to do. And it's going to be an algorithm called tournament pivoting. Tournament because it's going to run like a soccer match. You'll see it on the next slide. And so there are a bunch of different ways to do this that we explored, and we finally found a good way. And so let me just show you how it works. So here's a cartoon. And so to make it easy, let me suppose I have 4 processors, and each processor owns 1/4 of the rows of the matrix. So processor 1 owns W1, that's n over 4 rows, and so forth. And so what I want to do is do one reduction, and their b columns, is pick the b most linearly independent rows from all of these. So the first step in the algorithm is that with no communication at all, each processor will independently run Gaussian elimination with partial pivoting, the classical algorithm. So that means each one will independently be factored. And what does that do? Since I'm doing partial pivoting, each processor will pick the b most linearly independent rows from its local rows, right? So the top b choices from this permutation are going to be the most linearly independent rows of W1. I'll call them W1 prime. So that's going to be, this is, if you like, the quarterfinals in my tournament. So everybody chooses the best B players. So now it's time for the semifinals. And so what I do is I take the best B rows from processor 1, the best B rows from processor 2, I put them together in a game, and I run Gaussian elimination again. And I eliminate, and I pick the best B rows from these 2B, and I'll call those W1 2 prime. And similarly, I'll pick the best B from those 2B rows, and I'll pass those up the tree. Now it's time for the finals, and I take the best B rows from processors 1 and 2, the best B rows from processors 3 and 4, put them together, do Gaussian elimination with partial pivoting one more time, and pick the best B rows from all the processors. And so what do I do with those rows? I go back to my original matrix, which I have not overwritten, and I put all of those B rows at the top and do Gaussian elimination one more time with no pivoting. So because I picked the best B, so I just put them up there. And so that is going to be the algorithm we use. This does not pick the same rows as Gaussian elimination with partial pivoting. It picks different rows. And so we need a new theorem that says they're numerically stable, and I'll let you read that paper if you like. Okay. So let me now, in one cartoon, tell you what I've done. I've basically called MPI reduce, and my reduction operation is LU decomposition. That's all I'm doing is a reduction. I take a matrix from one child, a matrix from the other child, do LU, pass it up, do LU, pass it up. Okay? So that's the parallel algorithm I just showed you. But I also want to minimize communication in the sequential case, right? So I want to have something that minimizes the number of times I copy data from slow memory to cache. It turns out it's going to be exactly the same algorithm, except it's just going to be a different reduction tree. So here's the algorithm that's sequential. So suppose I can only fit 1/4 of my rows into cache at one time. So I'll read the first 1/4 of rows into cache, do LU, pick the best B. Then I'll read the next 1/4 of the rows into cache, put those B columns on top of those, do Gaussian elimination one more time, and I'll get the next best B rows. Read in the 3rd 1/4, read in the 4th 1/4, and when I'm done, I've read in the matrix once, 1 is the lower bound, from slow memory to fast memory, and I've gotten the best B rows. Now what if I have a different architecture, like dual core? So I could read in these two, run them in parallel, and have a little tree there, then read in the next part, then read in the next part. But what if I have a real machine, multi-core and multi-socket and multi-rack and multi-site and all that sort of thing, what a real computer is? No problem, I'm just going to choose my reduction tree dynamically. No matter what hardware I'm given at runtime, I will just pick the right reduction tree to minimize communication. And it may be that I get a different answer every time I run it, but hopefully it's still a good enough answer. So, so now let me say that this idea works for more than just Gaussian elimination. It's exactly the same picture for, for QR. So all I've done to go from this slide to this slide is I've changed the words LU to QR. So now my reduction operator, so now what is a QR decomposition? I want to factor a matrix into the product of a orthogonal matrix times a triangular matrix. And it's exactly the same idea, except now my reduction operator is taking a bunch of rows and factor them into 2q times r, pass them up, factor them into 2q times r, and it's all the same idea. And this is also the first step of the SVD. If you want to do the singular value decomposition of a tall, skinny matrix, this is exactly what you do, and then you do the SVD of this little r guy. So that's the basis of the algorithms for a bunch of linear algebra. So now let me show you some performance data. And so let me compare it to Scalapack first. And I'll show you both just the tall, skinny LU, and then if I use that as part of a square LU. So this is doing this tournament pivoting on a really tall, skinny matrix. So 1 million rows and 150 columns, and it went up to 4.37 times faster on this IBM Power 5. On a Cray XT4, I think a predecessor of Hopper, 5 times faster. Now, when you put that inside the overall Gaussian elimination routine, it makes it go faster, but not as, I still have all those other matrix multiplies going. And so now it was only factors of 2 times faster. So, but it's still worth doing. So what about QR? So here I have some more performance data. So on an Intel Cloverton, that's an 8 multi-core processor multi-core, it was 8 times faster. That's as good as you're going to get on an 8 processor machine. So here on a, this is a cluster with a commercial Dolphin interconnect network running MPitch that was 6.7 times faster than the previous version on 16 processors. On a Blue Gene L, it was 4x times faster on 32 processors. On a GPU, it was 13 times faster. So that was, I don't want to go into the details of how it worked, but that went a lot faster. Now this was an interesting experiment where the matrix was spread over 4 French cities connected over the internet. That's called the grid. That is another model of computing. So you can imagine how long it takes to send data between different French cities over the internet. It's very slow. And so here, it went 4 times faster on 4 cities. That's perfect speed up, right? Because it did all local kind of work, and then it had to send very little data to the one common processor to finish the job. And there's also an implementation in the cloud in using MapReduce. And it basically costs 2 MapReduces, 2 calls to MapReduce. And one call to MapReduce is an obvious lower bound for pretty much anything. And so 2 MapReduces is pretty close. So probably the best speed up was infinite. And so how do you get an infinite speed up? So in this case, what we did was we took the classical code for a matrix that was so big it didn't fit in DRAM, right? That meant it had to use virtual memory. It had to use disk. And we waited for a while, but it obviously wasn't going to finish, so we stopped. And then when we ran the new algorithm, it was only 2 times slower than as though we had infinite DRAM. So even though it still had to go to disk, it only had to go to disk once. And it turned out it was just 2 times slower than infinite DRAM, and so that was a big speed up. And again, these would be the same speed ups that you would see if you were doing the singular value decomposition on the same tall, skinny matrix. So now let me show you some predictions of how much faster this is going to run on a machine where we haven't implemented it yet. This is, again, something you could do. So this is a model of a petascale machine. We actually have a petascale machine now, but at the time we did this modeling, we didn't. And so what I'm doing here is I'm using a performance model, counting flops, counting words, and so forth, and I'm multiplying them by these parameters, seconds per flop, seconds per word, and so forth. And I'm comparing the Scalapack routine to the new routine. And I'm doing it for a whole bunch of different values of processors. So this is on a log scale, so 1 processor up to 2 to the 14th processors. And this is the log of the dimension. So 10 cubed, 10 to the 4th, 10 to the 5th, 10 to the 6th. So large number of processors. And at each block, what I do is I take the models, I say how much faster is the new code than the old code, and I color code it by the speed up. So dark blue, speed up is 1, no benefit. Up here, dark red, speed up is 80. Okay? So let's just sort of see what this says. Up here, where it's all dark blue, that's the Landau impact benchmark. I filled up the matrix. So why is this white? It's because the matrix doesn't even fit in memory, right? So these are the largest matrices that fit in memory if I only use that many processors. And up here, it's totally dominated by the n-cubed flops. Minimizing communication doesn't matter, so there's no speed up. The speed up is down in this corner, where you take a relatively small matrix and you use lots and lots of processors on it, so that the communication is what's dominant, and there you can get these large speed up numbers, potentially, right? So to be measured. And so it's strong scaling is you fix the problem size and you increase the number of processors. That's going from left to right, and that's where the benefits are likely to be. Okay, so now let me summarize the rest of linear algebra in one table, sort of tell you what we think we know. And so I'm going to have one table for what we think we know in the sequential case, and another table for what we think we know in the parallel case. And so what I'm going to do is tell you whether, what algorithms exist that minimize communication, either for 2 levels of memory or for multiple levels of memory. And I'm going to separately do the Blois and Koleski, so that's Gaussian elimination with no pivoting, if you like. Then LU with pivoting, that's what I spent most of my time on. And then I'll talk about the QR decomposition, least squares, and there's another version of it called rank revealing, which people sometimes want to do, pick the most linearly independent columns. And then the eigenvalue problem in the SVD. And I'm also going to distinguish between the number of words moved, does the algorithm minimize that, or does it also minimize the latency cost, the number of messages? Because some only minimize that, but they don't minimize that. So here's kind of a summary. I don't expect you to read it all, of the state of the art, and what these entries are the papers that sort of either first or most recently figured out how to do it. And so for Blois 3, we talked about that in detail last time. There are all these blocked and recursive algorithms, and they work either for 2 levels of memory or for multiple levels of memory. Oh, and what's the color coding? If I underline it, that means it's cache oblivious. It's just recursive. That's the simplest thing you could do. If it's green, it's something that we invented. And if there's a question mark, that means we don't know. Okay, so future work. So what about Koleski? LAPACK actually does hit the lower bound for the number of words moved if you pick the right block size, but it does not hit the lower bound in the number of messages. And various other people have figured out how to do that, and they all work for multiple levels of memory. LU with pivoting, I told you about, LAPACK does it sometimes if the matrix is really enormous or really tiny, but it doesn't do it in the general case. Toledo 97, that was the divide and conquer algorithm, split the matrix into left and right. And then this is the tournament pivoting version of it. And then here is the version where we figured out how to do minimize latency too by switching the data structure back and forth between column-wise blocked, column-wise blocked. Now, what about QR? Same story with LAPACK. If it's really enormous or really tiny, it works. There is also a divide and conquer algorithm that splits the matrix into left and right that minimizes the number of words moved, but it doesn't minimize the number of messages. Somebody else figured out how to do divide and conquer for least squares, where you divide the matrix into 4 submatrices, but it actually triples the number of floating point operations. Now, if you're only doing theory, that's fine, but a factor of 3 in the number of floating point operations, if your matrix is so small it actually fits in cache, you'll notice a factor of 3 slowdown, right? So that's not the best thing to do. And so we had this other version that fixed that. And then again, versions that also work for multiple levels of memory. So for eigenvalues in the SVD, those are much more challenging. LAPACK is nowhere close for anything. It sort of, it does n cubed memory movement, not n cubed divided by m or m to the 1/2, just n cubed. And so there are 2 situations: the non-symmetric eigenvalue problem, that's the hardest thing to do, and then the symmetric eigenvalue problem and the singular value decomposition. So we know what to do, and it's pretty efficient for the singular value decomposition and the symmetric eigenvalue problem, but we don't have good implementations yet. They're in progress. For the non-symmetric eigenvalue problem, we have something that in theory works. It's a randomized algorithm. We don't know how to do it without randomization, but it does, the constants are pretty nasty. So it may not be very practical, but anyway, so that's also think about as a class project. Okay, so that's the summary of the sequential case. Let me now give you a similar summary of what we know in parallel. And so let me remind you of the lower bounds that we're trying to attain. So I'm going to assume I have n by n matrices on p processors. First, I'll tell you about where I use as little memory as possible, right? We know we can use more, but let me do the standard case. N squared over p, memory per processor. And these are our goals, n squared over root p words moved, and square root of p processors. And so what I'm going to do is fill in this table. And what I'm going to do is for all of these different algorithms, I'm going to tell you how close I get to the lower bound. So I'm going to have a factor in here, which is the factor by which I exceed this, right? So if there's a 1 in there, that means I win. I've hit the lower bound. But if I have a factor of n in there, that means I'm n times way the lower bound. So let me just tell you first about scale pack, and then in fact, matrix multiply. Matrix multiply hits the lower bound. And the first person who figured out how to do that was Cannon's PhD thesis a long time ago. Now, scale pack actually comes within a factor of log p of the lower bound just for the bandwidth cost, even for the symmetric eigenvalue problem, but not for the non-symmetric eigenvalue problem. It's a factor of square root of p worse. But it's not so bad being only a factor of log p worse than the lower bound, but that's just for the bandwidth cost. For messages, it's a lot worse. And so you see there are these factors of n in the number of messages. So we're n times log p over root p worse than the lower bound. So this is why we were motivated to do better in the number of messages. So that's scale pack. And so here are the new algorithms, which have been invented recently. And they all come within a factor of log p, or well, log cube p, there's some theory there, of the lower bound. And so there's all sorts of class projects there to think about what to do. And we actually have a big grant to sort of update all of Scale-Pack and get these out there. But there's a bunch of things to explore in the design space. So now let me ask if we can do better. By using multiple copies of the data, we saw we could do that for matrix multiply by using C copies of the data. I could get the lower bound for the number of words moved to go down by a factor of square root of C. And for matrix multiply, I could get the number of messages to go down by a factor of C to the 3/2. So what can we do for, in this case? Again, we can come close to the lower bound. So let me leave the last two lines out for a moment. So matrix multiply, we did that already. We hit the lower bound, some log p factors. Polylog p means either log p or log squared or log cubed. I don't want to distinguish. And Koleski works, and Gaussian elimination works, and the QR decomposition works. But we couldn't hit this lower bound for the number of messages. We were bigger by a factor of c squared. In other words, making multiple copies of the data, then this changed from p to the 1/2 to p to the 1/2 times the square root of c. It went up. So the number of messages actually got worse. That was sort of depressing for a while. But then we proved a new lower bound. And this is optimal. So if you want to minimize the number of messages, the best thing to do is have one copy, c equals one copy. That minimizes the number of messages. If you use more copies, the bandwidth goes down, but the latency has to go up. In fact, what the theorem says is that no matter how you organize it, the product of the number of words moved and the number of messages has to be at least n squared. So if one goes down, the other has to go up. And so we do have algorithms that attain this. And we think we probably have algorithms for these, but again, that's work in progress. And so there's lots of class projects. OK. So I have a few minutes left. And at this point, I think we need to vote, because I don't think I have time to do all the topics. And so one thing I could talk about is multi-core. What are the special things that people do to make these algorithms run fast on multi-core? What's the infrastructure that had to get built? And I could also talk about GPUs. Or I could go back and do the proof of why the lower bounds exist. So I think I'm going to ask for a show of hands. And so how many people want to do multi-core? So 1, 2, 3, 4, 5, 6, 8. How many people want to do GPUs? I think that's going to win. Keep them up. 1, 2, 3, 4, 5, 6, 7. OK, and how many people want proofs? OK. So just so you know, the last time I did this, multi-core won. I don't know why. So. OK. So what I'm going to do here is talk about a former GSI's Best Student Paper Award. This was Vasily Volkov, who figured out how to do this well for the first time back in 2008 at supercomputing. So here is the issue. the GPU has a much more complicated memory hierarchy. It's not like L1 is inside L2 and you get to sort of hierarchically nest things like that. And it's also the fact that the GPU does some operations very fast. I mean, it's great at matrix multiplies, but it's not good at some of the other parts of the algorithm, some of the BLAS2 and BLAS1 operations. And so what we need to do is divide the labor between the CPU and the GPU. But we have to do that quite carefully because, of course, it takes time to communicate, move data between the CPU and the GPU. So all of those came up. And the other fun part is that the CPU and the GPU like different data layouts. You can't use the same storage format in both. So you have to keep moving back and forth. So here is the motivation. So back in 2007, this is old data, NVIDIA released the cuBLAS. And so here is some of the performance data for it. So here is the gigaflops, so going right is faster. So here was the peak speed of doing a Saxby compared to the Core 2 Intel Quad machine to which it was attached. So obviously it wins there. Now, if you asked it to do matrix multiply, it was also a lot faster than MKL, but it wasn't nearly as much of a speed up as that. And if you just took that algorithm I showed you and made it all run in the GPU, the blocked Gaussian elimination, it went slower than the CPU. So clearly, something was wrong. We needed new ideas, and that's what this paper was about. And so we needed to understand the GPU architecture in some detail. And the result was new, faster variants of all these different routines, but also sort of new coding recommendations, because they had certain recommendations in the CUDA manual which turned out to be inaccurate. So here is the memory hierarchy, and I think we've already seen a picture of this. It's changed over time, but there was a register file, and then there's a shared memory, and the register file has a lot more stuff going on in it, and you can there were 64 lanes of parallelism at the time. And a single operation, like a Saxby, could take one operation from the shared memory, another operand from this, and then put the answer back in there. So when you executed code, only some operations could be in the shared memory. So here are the basic ideas that Vasily came up with in order to minimize the time. So this is fairly obvious. Minimize communication with the CPU memory. That costs a lot. Keep as much data in registers as possible. That's the largest, fastest on memory, and just do vector operations. Use as little shared memory as possible, because it turns out that if you do have one floating point argument in the shared memory, you only can get 66% of peak, right? So maybe that's going to be the best you can do, but you can't go at the full speed of the machine if you use that shared memory. And then it turns out that vector lengths of 64 was a winner, as opposed to a much longer vector length, which is what they recommended, of 512. And so taking longer vectors and what's called strip mining them, breaking them up into many shorter vectors, went a lot faster. And the final code that he invented was, for matrix multiply, looked very similar to previous sort of vector codes. And so here, I'm not expecting you to read this, is the entire optimized matrix multiply. It fits on one slide. And so this was sort of the first building block that he did. So let's compare it with the code that NVIDIA distributed. So here was cuBLAS, which was running at 37% of peak. Now the peak speed is, if you have one operation in shared memory, remember, you can only go at 66% of peak. And if you want to get everything running, you really do have to use shared memory. It was impossible not to. And so 66% is the best. Vasily got to 60%, and the cuBLAS was only at 37%. So that was the first good idea. And so let me just put that up here. So here is the peak of Saxby if you did not use shared memory. There's the 66% for shared memory. There is the matrix multiply, which was quite a bit faster. It's going from 37% to 66%. And now the Gaussian elimination, if you now use Vasily's version of matrix multiply, it was now faster, but there was no big speed up. So there's still a lot more to do. So let's sort of figure out where the time goes. And so first thing is that row pivot, doing the row pivoting turned out to be very, very slow. This took half the time to actually exchange rows. And this is the S-swap subroutine in cuBLAS. And so so the vertical axis is time, so down is good. Horizontal axis is n. Here is when you store the matrix in row major layout, So you take one row, it's in consecutive memory locations, and here's when it's stored in column layout, which is what which is the natural algorithm because you're processing the matrix by columns. And there's a factor of 40 difference in the layout. So you really want to use a row-wise layout on the GPU. But that's going to be terrible for partial pivoting as you look down a column, because when you look down a column, they're going to be in separate, they're not going to be consecutive. Okay? So that's going to lead us to use different layouts on the CPU and the GPU. So here is the other problem, which is that when you call BLAS1, it takes a certain amount of time just to sort of send the command to the GPU and say, please run BLAS1. How long does it take? About 4 microseconds. So just to call a subroutine takes 4 microseconds, and your n is enormous, and it's sort of trivial the time it costs to do 4 microseconds startup. So you can't afford to call the BLAS1 very often at all because you'll be having all these 4 microsecond overheads. And so what you really can only afford to call big things on the GPU. So here is the panel factorization. So this is the time it takes to factor a tall, skinny matrix with 64 columns and n rows, where n is a horizontal axis, so up to very big matrices. And the vertical axis is gigaflops, so up is good. And the blue is the GPU time to do it, and the black is the CPU time. The CPU is much faster for factoring a tall, skinny matrix and doing all of those, BLAS1 and BLAS2 operations, up to a size of, like 1600. And so what we're going to do is to, do the panel factorizations on the CPU and then do the other part on the GPU. Okay, so we're only going to use the GPU for matrix multiply. We're going to factor the panels in the CPU. We're going to overlap the CPU and the GPU work. So the GPU is going to be doing the matrix multiply from the last panel while the CPU is factoring the next panel. So we're going to get parallels in that way. We're going to convert on the fly between the column major layout in the CPU and the row major layout in the GPU. Now, here's a change in the numerics. So when I update the upper triangular factor, I would use the classical ways. I do triangular solves, I do substitution. That's too slow in the GPU. Instead, I'm going to explicitly invert the triangular matrix and multiply by it. That is a different numerical property. So the CPU needs to double check to make sure that the triangular matrix isn't too nasty numerically, and that's very unlikely. And then we'll simply invert it, send it to the GPU, and the GPU will do a multiply instead. And so let's just look at the performance. And so here is the performance, including fraction of peak. So for Gaussian elimination, Koleski, and QR, and you can see now we're getting 49% of peak, and it is quite a bit faster than running it on the CPU. And it's and this is for doing 2 GPUs. Sorry, this is a different GPU. This is a different GPU than that one. That's an 8800, and this is a 280. So different models, and so that one goes quite a bit faster. And if I just do the speed up, and I compare it depending on the dimension of the matrix, it's not until my matrix is big enough, like 1,000 by 1,000, when I get a speed up over the CPU. If the matrix is smaller than 1,000 by 1,000, then I might as well just keep it all in the CPU and not bother using it. So now we can also ask, where does the time go? And so there's time spent. So if I look up here, let me look in the middle. Here's the time spent by the GPU. Here's the time spent where they're both working at the same time. So that's parallelism there. Here's the time spent transferring data side by side. And there's just CPU working all by itself. This dimension is bigger and bigger matrices. That dimension is a fraction of the time. So for big matrices, you're spending most of your time doing GPU computing, and that's fine. For smaller ones, it splits differently. So here is sort of saying how important were all of those different optimizations. So overlapping the CPU and the GPU, that got us up to like, let me get this right, a 30% speed up. Transposing row-wise to column-wise, that was a factor of like 1.9 for different matrix sizes. This is for doing all the pivoting. I didn't describe this in detail. So moving lots of rows at the same time. And this speed up of 40% was for changing triangular solve to matrix multiply. And so I'm sorry this is going so fast, but so now what's the final result when I do it? So here is 66% of peak. That's the fastest I can possibly do anything. Here's my matrix multiply. It's pretty close to that, 60%. And here's Gaussian elimination optimized quite well, and it's 85% of that particular peak. And so that is what you can do for Gaussian elimination and all the other routines on a GPU. So, and there's more work to do there if you like. So I'll stop now.